So you're all familiar with climate change and the science of climate change, and you've probably been watching over the years the situation in which the scientists keep telling us that we've got this colossal problem, and politicians, negotiators get together to try to address it and systematically fail. And there's this repeated disappointment about this mismatch between what the science is telling us we ought to do and what our politicians and negotiators are able to achieve. And what I'm going to do today is tell you about some recent work I've done that gives you a glimpse, kind of a systematic way of thinking about what the challenge really is for the negotiations, and also insight into why the negotiations have failed so far. This topic is so big and so complicated. I'm going to give this one talk about this one thing, but this is actually a huge research effort just for me, and there are other people working in the area. It's deeply complex, and there are a lot of things we understand, but there are a number of things we don't, obviously. Okay, and in particular what I want to focus on is the concern that scientists have expressed, and also politicians, that the messing around that we're doing with the climate system could actually trigger catastrophes. By the way, when I use the word catastrophe, I'd feel more comfortable if you thought of it as being in quotation marks, because I think we need to be open-minded as to what a catastrophe actually is. The focus of the negotiations from the very beginning, the Framework Convention on Climate Change from 1992, to which every country in the world is a party. I think the only non-party is the Holy See. Last I checked, that was true. So we could contact Rome and find out why. But I think everyone else is a party to the treaty. And what the treaty says in Article 2, very important, is that the world agrees that we ought to limit concentrations of greenhouse gases in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. And this word dangerous is drawing our attention to something that's not simply bad, but at least approaching what we might call catastrophe. Now, this was agreed in a very kind of qualitative way in 1992, and after that time, a number of people, but especially the members of the European community and then later the European Union, tried to quantify what we meant by dangerous interference, and they finally succeeded in doing that in the negotiation session in Copenhagen, in which countries recognized the scientific view that the increase in global temperature should be below 2 degrees Celsius. I should say, by the way, there is no scientific view, and that the politicians to some extent are hiding behind this. I'll come back to that in a minute. And then finally, I think the technology is working now. Finally, in Cancun, which was the international meeting that followed on Copenhagen, countries reaffirmed their wish to avoid 2 degrees C, but they also said they would consider strengthening the long-term goal on the basis of the best scientific knowledge, including in relation to a global average temperature rise of 1.5 degrees centigrade. So what they're basically saying is, we chose 2 degrees C, but we're not sure if that's the right number. We think actually it might be lower. And I'm going to point this out now because you'll see later when I develop the analysis, this is exactly what this work I'm going to present predicts. You actually propose to do less than you know you ought to do. And then after that, it gets even worse. The latest international negotiations on climate, at the Conference of the Parties, blah, 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 took place in Durban last December, in which countries reached a decision, one of which was to note with grave concern the significant gap between the aggregate effect of parties' mitigation pledges in terms of annual emissions of greenhouse gases by 2020. So these are the pledges that were requested starting in Copenhagen. If you add up those pledges, they don't meet the collective goal of keeping temperature within 2 degrees C and certainly not within 1.5 degree C change from pre-industrial levels. So you've got a mismatch, again, between what countries are proposing, what they think they actually need to do, and then they're pledging less than they need to pledge to get to the proposal. And we don't know what they're going to actually do, but what the theory and the experiment I'm going to discuss tell us is that they're going to actually do even less than they pledge. So there's this constant cascading down about what we want to do, what we propose to do, what we pledge to do, and what we actually do. And this is, I think, characterizes the negotiations that we've seen so far in the last 20 years. Now, you might be curious about the science and what the science says. There actually are a number of papers that have been written about the science of dangerous or catastrophic climate change. Most of this work, by the way, was written after the Framework Convention was negotiated and this notion of dangerous interference was brought up. It was not as if there was a scientific literature pointing to something that was dangerous before 1992 and the politicians responded to that. I think the direction is much more the opposite, that the politicians wanted scientists to tell them what to do, and then the scientists searched for an answer after the Framework Convention was negotiated. Anyway, there are a number of papers that have been written on this possibility of tipping effects, catastrophe, and so on and so forth. The one I'm going to mention here was one I heard about first in this building in one of the other rooms, and that's a paper that got a lot of attention by Johan Rockström and colleagues, including many friends. And while they recognized the importance of the 2-degree target as a politically stated target, they were proposing a climate boundary for the planet of 350 parts per million CO2 by volume in the atmosphere. Okay? So you might think in your mind that as being a kind of a target. There's a relationship between concentrations and temperature, but we don't need to worry about that right now. Okay, so the question I'm asking in this research is, does the prospect of crossing a threshold, or you might call it a red line, for climate change affect the incentives to cooperate? And it's kind of suggested in the way in which the negotiations were framed from the very beginning that countries thought that this might help them to negotiate a treaty. So that's the question. And again, I'm looking at the negotiation itself. This picture here was taken at the Copenhagen negotiations in December 2009. It may be hard for you to see, but this is President Obama, Sarkozy, Angela Merkel, and this is Gordon Brown. So there were a number of countries that met to discuss what they wanted to do. And the way I'm going to look at these climate negotiations is a little bit like this, but I'm just going to be a little cheeky and say it's actually a little bit like a card game. Now, I often use the cards as a metaphor for thinking about this, but it turns out for the work I want to talk about today, I'm better off with poker chips. So I'm going to tell you about how countries choose poker chips when they play the climate change game. Okay, now there are two kinds of climate change to think about. One is a gradual climate change, which means you get this kind of slow unfolding in climate change, with kind of a linear process. You throw a bit more greenhouse gases into the atmosphere, concentrations go up a bit, and that causes a bit more warming, which in turn causes some more damage, and so on and so forth. And that was kind of a conventional view, and what we're doing now is we're overlaying on top of that view the possibility that this accumulation of greenhouse gases in the atmosphere can trigger something that's nonlinear, something that's quite dramatic and sudden, the kind of thing you would want to include in a Hollywood movie like The Day After Tomorrow. Okay? So first I want to start off with this view of gradual climate change, and we look at it as a game. I'm going to just throw out an example and hope that you can follow it, because this is how I want to start with setting up a model for catastrophic climate change. So in this game, I have 10 different players. You can think about these people playing poker. Each has 10 poker chips, and each can contribute any number of the chips he or she has. And the amount of chips that each of the players wants to contribute depends on how much they think they're going to get back. They want to get the highest amount of money or payoff they can when they play this game. And I'm going to make up some numbers now. They're going to get a payoff of 10 cents for every chip they keep. So If you hold on to a chip, you get 10 cents. If you throw a chip into the pile, everyone gets 5 cents, including you. Okay? So to give you an example of how this works, suppose that you throw 4 chips into the pile, and all the other players throw in 45 chips. So there are 49 chips in total. The payoff that you get, well, you get 10 cents for every chip you held on to, and you're going to hold on to 6, because you started with 10, you threw in 4. Plus, you're going to get 5 cents for every chip thrown in, including the 4 that you threw in, and they're worth 5 cents each. So you add it up. The payoff you're going to get, if you play the game this way, is €3.05. Now, then you might ask the question, what's the best the group could do? Okay. Well, if everyone contributes all their chips, everyone gets €5. And it turns out in this game, that's the best they can do. So the metaphor you want in your mind is that you want all the countries to throw all their chips into the center of the table. But now you need to look at it from the perspective of individual players. If everyone else contributes, let's say 90, so in other words, there are 10 players, if 9 of them can throw in all their chips, then you ask, what should you do? You get €5 if you contribute all of your chips, but you get €5.50 if you contribute none. So the incentive is to contribute none. You think of it this way, every time you throw in a chip, you personally lose 10 cents, and you personally gain 5 cents, so you on net lose 5 cents. You lose for every chip you throw in, but of course the room as a whole, everyone together, does best if you throw in all your chips, because there are 10 of you. So the gain to the room is 50 cents, the loss to you is 5 cents. So this is a kind of a metaphor for thinking about what countries should be doing when they meet in these lovely places like Copenhagen and Cancun and so on. And this game is a very famous, probably the most famous of all games that we study in fields like economics, and it's called the prisoner's dilemma. The key thing about the prisoner's dilemma is that you've got these two different, you have a tension reflecting two different motivations. One is this temptation to want to hold on everything for yourself, and the other, just as important, is to recognize that if we all do this, we're all in bad shape. So you simultaneously want everyone to get together and to contribute, and also to hold back on the amount that you contribute. And I think that's the reason why countries meet again and again to try to come up with an agreement, and why, again and again, they fail. There are a lot of other things about climate, of course. I don't have the time to go into all the dimensions of it, but in my opinion, this is absolutely central. Okay. Now I'm going to throw in a new technology which will be useful later. So the chips we were looking at before were all black, but now I'm supposing you also get a pile of red chips. Okay? You have 10 of those. And the red chips, you get, just as before, you get 10 cents for every black chip you hold on to, but you now get €1 for every red chip you hold on to. Okay? And every chip you throw into the pile, doesn't matter if it's black or red, you still get 5 cents. Everyone in the room would get 5 cents each. So with 10 people in the room, everyone in the room collectively would get 50 cents for every chip thrown in. Now, if you contribute a red chip, that'll cost you €1, but it'll only give the room this aggregate benefit of 50 cents. So the room loses for every red chip thrown in. Okay? So this technology is something you don't want to use. Now you might wonder, why did I mention this then? Because that technology that you don't want to use in addressing gradual climate change may be a technology you need to use to avoid catastrophic climate change. Okay? And the technology to think of is something called air capture. It may be hard for you to see. This is a fictional representation of a landscape in which you have these machines here. These look to me like upside down fly swatters. And they basically are exposing to the air a chemical sorbent that will take carbon dioxide out of the air and store it down below ground. So it's a direct way of limiting the concentrations of greenhouse gases in the atmosphere. Over here you have windmills. So you might think of the black poker chips as being windmills, kind of conventional abatement, and the air capture machines as being this more expensive technology. And in fact, if I were to tell you about the economics of these technologies, the marginal cost, the cost of using air capture to remove a ton of CO2 from the atmosphere, we don't know the exact number. The range I've seen is from $40 per ton of carbon dioxide up to over 1,000. It's ridiculous, by the way. And if you want to address this problem seriously, you not only need R&D discovery into the science of climate change, but you also need to understand about the technological options that you can deploy to address the problem. So let's say that the cost maybe is in the neighborhood of around $500. Just sort of make up a rough number. Well, the benefit that the world gets by removing a ton of CO2 out of the air, well, we don't know exactly what that is, but probably a rough number you might think of would, the range that's out there might be somewhere between $10 and $100, say. So the point is that this technology is too expensive currently, as we understand the technology, for addressing gradual climate change. But the problem is, to address catastrophic climate change, we need technologies like this. And we'd be willing to pay them if the consequences of catastrophic climate change were so great. Okay, so that's why this is important. So this is, so now I want to turn to this question of catastrophic climate change. Maybe hard for you to see. This is where I live. This is New York, and in this image it's underwater. So you're just seeing the tops of the highest buildings. This is a way to think about catastrophe. If you wanted to go to 350 parts per million, as was recommended by Johan Rockström and his colleagues, we're already at over 390. So if you limit emissions, you're not going to stay within the boundary that they've set. The only way to get below 350 is to start to take the stuff out of the air. Okay? So the way to address catastrophic climate change now is you're going to have to deploy a kind of emergency measures to take CO2 out of the air. That's why we need that other technology. Okay, so now let's look at a game about catastrophe. And I'm going to just set this up like I did the other game and say that the threshold for avoiding catastrophe is that the players around this table have to throw in at least 150 chips in total. So they've now, each person has 10 black chips and 10 red chips. So each person has 20 chips, and there are 10 people in the room, so they have 200 chips at their disposal. If they throw in 150 or more, they avoid catastrophe. If they throw in 149 or less, they still experience catastrophe. Okay. And catastrophe, remember, in quotation marks, okay, here is 15 euros. Okay, not catastrophic, but if it makes you happier, you can multiply that by 1 billion or something. For the representation I'm going to give you here, it won't matter. Now, suppose everyone else contributes 0 chips. What do you want to do? The best thing that you can do if everyone else contributes 0 is to contribute 0. Because for you don't have enough chips to avoid catastrophe, and for every chip you throw in, you only get back 5 cents yourself. And each chip costs you either 10 cents or 1 euro. So you're always going to be worse off by throwing chips in. So one thing we know is, if everyone else throws in no chips, you want to throw in no chips. Okay? So that's one situation in which countries may find themselves. But now, and that was similar to the other game we looked at, without catastrophe. But now things are different. Suppose that everyone else, the other 9 players, throw in 135 chips. If you throw in 15 chips, you can avoid catastrophe. That changes everything. So if you throw in no chips, as before, you're going to get a payoff. You're going to get 10 cents for every black chip you hold on to, and you have 10 of those. And you're going to get 1 euro for every red chip you hold on to, and you have 10 of those. You're going to get 5 cents for the 135 chips thrown in by everyone else, but you're going to have catastrophe. And therefore your payoff is going to be 2 euros 75 cents. If you throw in the 15 chips to avoid catastrophe, your payoff is different. You're then holding on to 5 chips, and you're going to hold on to the expensive ones, the red chips. So you get €1 for each one of those. Then you get because of gradual climate change, mitigating gradual climate change, you get 5 cents for all the 150 thrown in, plus, sorry, that's it. You don't experience catastrophe. That's the key thing. You don't experience catastrophe. And your payoff then is going to be 12 euros 50 cents. And that's a lot bigger than this amount. So given that everyone else throws in 15 each, the best thing you can do is to throw in 15, and the world avoids catastrophe. So this is a very positive result. This should make us cheerful. It's a way to understand why the negotiations were framed in this way in the first place. This idea of avoiding danger. We all want to avoid danger, and if it's within our means to do it, we'll do it. So this is a very positive result. This kind of game is not a prisoner's dilemma. It's called a coordination game. It's a coordination game because it's not true that each of us wants to throw in 15 or 20 chips, whatever. We don't want to throw in 15 no matter what everyone else does. We only want to throw in 15 if everyone else throws in 15. So we require a little bit of coordination. I study lots and lots and lots of global issues. I am extremely confident that if this represented the problem, we would solve climate change. Because we solve lots of other issues that involve coordination. Okay? So it's helpful to use this as a benchmark for thinking about what the climate problem might look like with catastrophe versus without catastrophe. Just to expand on this, it turns out I gave you specific values for those. You need 150 for the threshold, 150 chips. But you know, maybe it's 149, maybe it's 161. Let that number vary. I told you that the consequence of catastrophe was a loss of 15 euro. Change that number. You know, maybe it's going to be 1 euro, maybe it'll be 100 euro. It could be different values. Well, here you have the threshold, which was 150. And here you have the impact, which was a loss of 15 in the example I gave you. What this picture is showing is that you can vary those two numbers, and you can discover when it pays for countries to coordinate, when they'll be stuck instead in a prisoner's dilemma, and when they just don't want to do anything to avoid catastrophe at all. Down here you don't want to do anything because you have to do a lot because the threshold is high, and yet the impact of catastrophe is very low. It's not worth doing. In a sense, it's not really a catastrophe. That's why I wanted to use that term, catastrophe, in quotation marks. Okay, so you can generalize. Now I want to look at the situation of uncertainty, which is the situation we face. And in particular, I want to emphasize the role of scientific uncertainty. Okay. Now, if you go back to the Rockstrom, and this is just one illustration of a way to think about this. If you go back to the Rockstrom et al. Paper published in Nature, they picked 350 parts per million because historically that was a level at which we have some confidence you could avoid loss of the major polar ice sheets. Okay? So that's what they are focusing on primarily. And when you read their paper, you'll see that they say the planet was largely ice-free until CO2 concentrations fell below 450 plus or minus 100. So there's a range of our knowledge about how to maintain stability of the ice sheets between 350 and 550. And what they did is they picked 350, a single number, so as to ensure the continued existence of the large polar ice sheets. So what they're doing basically is applying something that you may have heard called the precautionary principle. There's this range. Let's just choose the safe end of the range. Now that reflects values. So you might say, well, wait a minute, how do scientists get to choose those values? What I'm going to show you is that the logic they applied is correct. Even if we don't care literally about precaution in the sense of being averse to risk, it's still correct. That's a powerful result. I like that. Okay. Now, what I'm going to do is I'll just give you an example again. So before, the impact of catastrophe was that you lost 15 euros. But now I'm going to say the impact of catastrophe, well, you may lose 10, you may lose 20, you may lose any amount in between. Okay? And before I said the threshold is 150, but now I'm going to say the threshold could be as low as 100, could be as high as 200, anywhere in between. And for both those values, the probability of being in any one of those places is always going to be the same, so I'm using what's called a uniform distribution for probabilities. Now the theory, which I'm not going to expand on in detail here, predicts that when you have uncertainty about the impact, it has no effect on behavior at all. It doesn't matter. What matters, what drives behavior, should be what we call expected values. So here, if you had a range from 10 to 20, the expected value would be 15, and that would be what would drive behavior. The theory I have, which I will explain now because it's the more important result, is that if you have uncertainty about the threshold, this will be critical. And everything I just showed you is going to fall apart. Okay? Now, it's important to understand that that uncertainty about the threshold has nothing to do with values. It has everything to do with science. It's a purely scientific phenomenon. Okay. Oh, there's a nice metaphor to think about this. So forget the chips for a minute. A colleague of a number of us here, a close friend and a fellow of the Barrett Institute, Paul Ehrlich, wrote with his wife Anne a lovely book called Extinction, in which he starts the book with this story, this fictional story about someone coming to an airplane, to get on an airplane, and he sees someone working on the airplane popping the rivets off the wings of the plane. And he's worried that this is going to affect the safety of the flight. And he's basically using that as a way to explain what we're doing to the planet now. And you can think of that in terms of throwing greenhouse gases into the atmosphere. Okay? So why would you want to remove rivets from the wings? Well, in his representation, you want to do it because you can get some money by selling the rivets. Okay, it's a little far-fetched, but just try to believe that's true. And the question is, how many rivets can you remove and get away with? You know, if you take one rivet out, it's probably going to be safe. If you take too many out, it won't be safe. So how many can you take out? That's a way to think about this problem of uncertainty about what the threshold is. Okay, so now again I'm going to be specific like it was in earlier cases, and I'm going to look at the situation in which you make the world as well off as possible. Okay? We call this full cooperation. So imagine the countries were cooperating fully. It turns out that the best thing they can do would be to throw in 200 poker chips. They throw in all their poker chips. And therefore they reduce the probability of catastrophe to 0. That's the precautionary recommendation. And what's cool is that they want to do this even if they're not risk averse. So I'm going to explain to you now why they want to do this. So I've told you they're going to want to do this, now I want to explain to you why. If everyone throws in 20, all their poker chips to the center of the table, everyone's going to get 10 euros. So the payoff for the entire room, since there are 10 people, would be 100 euros. Okay? Well, suppose everyone else contributes 20. They throw all their chips in, and you're the last player, and you throw in 19. You hold on to 1. And the one you're going to want to hold on to, of course, is the expensive one, the red one. So you hold on to the red one. What do you get then? Your payoff then, you're going to get 5 cents for every poker chip thrown into the center of the table, and there are 199 of those, because you held back on 1. Now, because you held back on 1, there's a tiny probability, that's that one rivet you remove from the wing, there's a tiny probability that that choice of yours will trigger catastrophe. Okay? But the probability here is only 1 over 100. It's tiny. If you trigger catastrophe, the way I'm setting this up, it'll cost you 15 euros. You get 1 euro for holding on to that red chip. So your payoff then is 10 euros and 80 cents. And notice that your payoff to holding on to just one of your red chips is bigger than if you throw it in. Okay? The total payoff for the whole room in this case is 99. And that's less than if you throw your chip in. So what happens is if one player holds back on the chip, that player does better and everyone else does worse. The room as a whole does worse. Okay, what is this? It's Prisoner's Dilemma all over again. But what's cool about this is that the Prisoner's Dilemma wasn't constructed in the same way as the one we had with gradual climate change. It arises because of uncertainty and the threshold for catastrophe. That's what creates the problem. That's a very different way to think about the climate problem. Okay, now you may not be convinced by this. This is theory. So basically, well, it's cute, but is it true? Would real people behave this way? Okay. I can't tell you. I'm not allowed to interact with real people very often. But I discovered a wonderful researcher who does, and she was willing to collaborate with me. Her name is Astrid Dannenberg, and she has just come to Columbia as a postdoc. But she is an experimental economist. And she and I constructed an experiment that's very similar to the story I just told you here. And we played this experiment with real people. And we gave them real money. And we saw how they behaved. And I'm going to tell you now in summary form what they did. Okay, now just before I do that, we had these what are called treatments. So one is you have certainty about everything, which means about the threshold and the impacts. One, you've got uncertainty about the impact. One, you've got uncertainty about the threshold. And the final one is you have uncertainty about both the threshold and the impact. Okay? Now, the theoretical model predicts that so long as you have certainty about the threshold, you're going to have a coordination game, not a prisoner's dilemma. The prediction is catastrophe would be avoided. And the numerical prediction is that countries will contribute exactly 150. If you have uncertainty about the threshold, the prediction is that you will then have a prisoner's dilemma game. That's bad. You will not avoid catastrophe. That's obviously bad. And the total contributions will be zero. Now, I should tell you right away that when you play around with these games, we know, because of the large body of literature out there, we know when to take a game very seriously and when not to. Okay? I never took literally the conclusion that no one would contribute anything, because I know experiments like this have been done many times over and people do contribute something. Sweden I can pretty much count on to contribute to a global public good. I think if the whole world acted like Sweden does on a lot of issues, we would probably be much better off. But unfortunately, the whole world is not Sweden. So I'm looking here at the rest of the world here. And again, how real people will behave. Here are the results. So we did this experiment with people in groups of 10 using the same values I presented before. Now, what the theory predicts, it basically is in these two treatments here. This is certainty about everything. This is certainty about the threshold, but uncertainty about the impact. Theory predicts that you should have catastrophe here. In other words, everything should be blue. Well, when you look here, almost everything is blue. That's pretty good, actually, I think. So 18 out of 20 times this game was played with different people, 18 out of 20 times you had catastrophe. There were 2 times, sorry, you avoided catastrophe. Forgive me. You avoided catastrophe. This is when you have certainty about the threshold. So you know what to stay clear of, right? The 150. So only twice did you have catastrophe. I think twice is pretty good, but if you look into the reasons, it's more interesting than that. It turned out that in each of those 2 groups of 10, there was one person who was mischievous in his or her behavior. One person in each group. And this person said that he or she was going to contribute a lot and didn't. Now, in some games, when someone tells you something, you know not to believe them. In this game, they have a reason to believe them. But these 2 people disappointed them. What I want to emphasize is these are 2 people out of 200. So 1% of the population consisted of bad apples. Now, I don't know about your experience in life, but the ratio of bad apples in my own personal experience is above 1%, so I was pretty pleased by this result. Now again, if the theory were right, in these cases in which you have threshold uncertainty, and where the theory says it doesn't matter if there's impact uncertainty or not, I would expect everything here to be red. That is, that you would have catastrophe. Now it's almost true that everything is red, but what happened is that in these 4 cases here, a little bit of effort was made to throw in enough chips, as it were, that you had over 100 chips thrown in. So you made some small reduction in the probability of catastrophe. The best they ever did, by the way, was to reduce the probability of catastrophe from 100% down to 80%. So still high. That's the best, and that was only done by one group. Okay? So the basic prediction from the model seems to hold up well as a qualitative phenomenon. Now we look into the numbers a little bit. These are a numerical representation of some of the results. And I know it's a bit bewildering when you see numbers. I don't usually use numbers, but then I have this colleague who can do the experiments. Okay, the main thing to focus on is numerically the model predicted that you would get exactly 150 contributed in the certainty cases, right? Certainty about the threshold. And these are the average contributions over the games we play, the 20 games with certainty. And you can see they're very close to 150. In fact, statistically, there's no difference. Now, the model predicted 0 contributions for the threshold uncertainty cases. You don't get 0. You get more than that, and that is also statistically significant. Now, intuitively, what's happening here is those black chips are cheap. They only cost you 10 cents each one. And it's true you lose 5 cents, but come on. 5 cents, that's not much, right? So we're talking about German students playing, and even for them, 5 cents isn't much. So you could be generous at very little personal cost. That's basically why you're getting that. What isn't happening here is that they're not throwing in all their black chips, and they're not throwing in any of the red chips. So there's no way that they're going to avoid catastrophe. If you look a little more carefully at the table, I guess that looks kind of, well, it looks kind of like the Olympic sign. If you look a little more carefully, you'll see the amounts that are proposed, almost exactly 150 on average, and they correspond very closely with what's actually contributed. So this is a situation in which negotiators are truthful. It happens sometimes because it's in their interest to be truthful under those circumstances. Here it's different. Now you notice when you have uncertainty about the threshold, the amounts that are proposed, they know, and I'm going to come back to this later, they know they should go to 200, as I explained before, to avoid any prospect of catastrophe. They know that. What they tend to do is they go to about 167. They underplay it. Okay. So here you get a big difference. And then, as you move in this direction, of course, it drops. So that there isn't the same correspondence here with the amounts that are pledged, or the amounts that are proposed, rather, for the group. The amounts that are pledged, these are promises by individuals, right? If you multiply these by 10, you get numbers that are significantly lower than over here, and most especially by the numbers that are actually contributed, a lot lower. So you're getting very big differences, even quantitatively, between the situations with and without threshold uncertainty. So to summarize, threshold certainty about catastrophe changes the game. With gradual climate change, you have a prisoner's dilemma. With threshold certainty and the prospect of catastrophe, you have a coordination game. The international system is very good at dealing with those situations, which I think helps to explain why the negotiations were framed in this way. Uncertainty about the threshold, however, takes you right back to a prisoner's dilemma. And that, I think, is explaining why the negotiations are not succeeding. This is interesting. Relative to the certainty case, certainty about the threshold, uncertainty about the threshold requires that more abatement be done. So if you pay attention to Johan Rockström, you want to do more than you would have done. Take into account uncertainty, right? You would want, suppose that he said that it was 450 plus or minus 100. So instead of wanting to get to 450 ppm, you want to do more to go to 350 ppm. But actually what happens, and what's predicted, is that countries will actually do less. So you're being pulled in your logic for what you should do collectively is going in one direction, and your incentives for behavior is going in the opposite direction. It's pretty startling. In terms of behavior, and this is the kind of insight that only comes out of experiments. You can't get this insight from theory. Astrid, did an interview with through a questionnaire of everyone who played this game. That's 400 people. We know, based on that interview, those questionnaires, that they knew when they played the uncertainty game that they should go to 200. They knew that. Okay. But when they made a proposal to the whole room, very few of them actually proposed 200. On average, most of them proposed 165. So it's a bit like, I know what we should do is we should avoid something like 1 degree C, but I don't think I'll be taken seriously, so I'm going to propose 2 degrees C. That's the way to interpret that. Okay? And then we look at their pledges. They add up to less than they propose. So that's why I think countries can go to Cancun, to Copenhagen, say we should avoid 2 degrees C, and then when they make their individual pledges, understand that when you add them all up, you'll never avoid 2 degrees C. That's exactly the situation we face right now. And as I said before, we don't know what countries are actually going to do, right? We only know what they've pledged. So maybe they'll do everything they pledged. If you're a cynic, you might be thinking, well, maybe they won't. Well, what the theory predicts is that they won't, and what the experiment shows is that they won't. What happened in the experiment, they said they were going to contribute 155, they only contributed 78, and that meant the catastrophe took place. In fact, in every case, when we actually played the full game, including the random element about triggering catastrophe, in every case, with certainty about the threshold, in 18 out of 20 cases with certainty they avoided catastrophe. In every case in which you had uncertainty about the threshold, ex post, there was always catastrophe. That's a very negative result, which is why you need a little humor, you know, because you have to keep your sanity. So what does this imply about when we will succeed? This is a cartoon. I can't remember where I got it from. But you have here the arc, and these are the climate negotiators, but they're meeting in 2040 atop Mount Everest. Apparently the only land that's available, Manhattan's long covered up. And the head of the conference says, good news, we finally have a binding international agreement to control greenhouse gases. In other words, it looks like if you take this, this story I've told you seriously, and you take the science seriously about the possibility of catastrophe, we will trigger a catastrophe. Now, the policy implications. So long as there exist irreducible uncertainties in the climate system, and they do. I mean, we're playing an experiment. We don't, with the planet. I don't mean with undergraduate students. I mean with the planet. We don't know exactly what's going to happen. Identifying a threshold to avoid something we're going to call dangerous interference is not going to promote cooperation. So what the research is suggesting is that the strategy of focusing on a number for dangerous or catastrophic climate change is not going to work in advancing cooperation. We should try other strategies. So now, in the last 1 minute of my talk, I'm going to be more positive. Because so far what I've done is I've presented a very negative result, but I think I've also shown you how to interpret what it is we're reading about in the newspapers. So when I say we should pursue other strategies, what do I have in mind? One of the insights of this work is that if you could, you would like to be able to create a coordination situation. Well, Mother Nature is not doing it for us. That's what the research is showing. So it's up to us to do it. How do you do it? There are two possibilities I've thought of. I'm going to try to come up with some more. I hope you beat me and come up with ideas of your own. One is through the application of trade restrictions. I don't mean in a kind of a general sense. I would disagree with almost every proposal made for trade restrictions I've read so far on climate. However, I do think there can be an impeccable logic to wanting to use trade restrictions under very special circumstances. Okay? And the logic of this is that if there's an agreement over some kind of behavior, and that agreement says that the parties are not allowed to trade in that sector covered by the agreement with the non-parties, then what happens is, as there are more and more parties, the non-parties become increasingly isolated and they lose the gains from trade. And that creates an incentive for them to want to join and do what everyone else is doing, that is, buy into the free trade agreement. Now again, that only would apply under certain circumstances, so don't think that this is an easy answer. But I would say that while I'm an economist, and while economists are generally positively disposed towards free trade, in this case, of course, you have a colossal market failure at the planetary level. And it may be the case that trade restrictions would be helpful. And the last thing I want to say about trade restrictions is, I'm almost done, about trade restrictions is the beauty of this idea as opposed to everyone else's idea on trade restrictions is that if the threat to use the trade restrictions is credible, you will not actually have to restrict trade. Now you might say, well, this is pretty fanciful. It's not, because we did the same thing in another treaty to protect the ozone layer, the Montreal Protocol. That was how that treaty was enforced. Okay? It included trade restrictions. Trade did not actually have to be restricted, but if you pulled the trade restrictions out, I'm very confident that agreement would not have succeeded. Okay? But you can't just replicate Montreal for climate. It's much, much more complicated than that. So this is not a general statement I'm making, but something to be very specific. The other way in which I think it might work is if you had an agreement over technical standards. Now, economists, for some reason I've never understood, seem not to like technical standards. In fact, there's quite an opposition to it, as if choosing standards, particularly if governments are involved, probably in Sweden this wouldn't bother you too much, but in other countries it does, that this is somehow picking winners, and it's a very bad thing to do. That's ideological. I don't think there's any place for that in research and science. You have to ask the question, might this be a means to an end? And what we're thinking of is the second best. Maybe not the ideal, but maybe it's the best that we can do. Well, the thing about technical standards is usually you choose them because there is an incentive to coordinate. Okay? The idea here would be that you would choose a technical standard not for the purpose of coordinating for commercial reasons, which is the usual purpose, but you would choose it strategically because you know that by choosing that, you're going to cause everyone to use a new technology that they wouldn't use otherwise, and that new technology would be instrumentally useful in lowering greenhouse gas emissions. Okay? Now, where it really would work most powerfully would be if you have so-called network externalities. What this creates a situation in which the more people who have a certain technology, the more you want to have that technology. Okay? And we do create standards already for these kinds of technologies, but what we haven't done is created standards for the purpose of promoting the supply of a public good that would be associated with the technology. That's where the logic is different. That's the strategic logic. So I'll end with those two more positive statements, that we can take the logic from this paper and we could apply it to climate change. There isn't a simple solution, at least that I've thought of, for dealing with climate, but we can pick at this problem and make much more progress than we have so far. Thank you.